So today I want to talk about some of the dialing work that we've been doing with respect to for primarily for data. So before I show the results itself, let me take a quick intro. So the code that we work with is called Spectral. So Spectral is a suite of spectral element codes that is used to simulate wave propagation through heterogeneous media. Essentially, we use it to simulate earthquakes and compare the synthetics to realistic data for inverse simulation. Like the code has been in active development since '99. It's a code package that is divided across
It's a Kotlin package that is divided across 3 repositories, 2D, 3D, and 3D globe. It's heavily utilized. It has about 32,000 citations, about 30 to 40 contributors over its lifetime. As I said, it's written in Fortran 90, and it runs on CPUs, obviously, but it also has GPU ports with CUDA and HIP. Now, the project that I work on is called SPECFEM++. So it's a complete rewrite of the Fortran packages. Essentially, we wanted to integrate the 3 different packages, 2D, 3D, and 3D globe, under a single interface, and using Kokkos, run it across different architectures. So obviously, we're using C++ and Kokkos. Now, let me dive into the problem statement itself, right? At the end of the day, what we're solving is a wave equation. The PDE looks something like this. If I look at the weak form for a fluid media, there are 3 terms. Let me focus on the middle term, which is the most computationally expensive. The assembled system looks something like this. There are essentially 3 main things going on here. The first is the gradient operator. Next is the stress computation. Third is the divergence operator. And all of this is embarrassingly parallelizable because we can loop over this summation. Now, the only thing that changes across different media, let's say this is for a fluid media, let's say if we wanted to implement a solid media, is how we compute the stress, right? Everything else can be templated on the number of components of that media. So in terms of optimization, this becomes much simpler because now the compute bound functions are essentially the gradient and the divergence operator. So let me focus on the gradient operator. The pseudocode looks something like this. It's a bit tedious, but at the end of the day, what we're doing is 2 small gems. That is F times L prime and F transpose times L prime. That's the main thing to understand. Now, let me digress a bit here. So SpecFem++, it's a large code base as of right now as well. It has a rich feature list, which is on the right. It has about 90,000 lines of code. It's a C++ solver with a Fortran mesher, and it's heavily templated. So I wanted a playground to experiment and see how far I can optimize the gradient operator. So, and the main reason being that the performance bottleneck is in few functions. One of them is the gradient operator. So we set up a playground, and that's listed here. So all the results that I'm presenting today is within this repository. So first, let's look at the easiest way of parallelizing things in Kokkos, right? So I have these 3 for loops, which are embarrassingly parallelizable. So I split them over either range policy or MD range policy. In range policy, I split up my own index. We see that here are the performance curves for that. We see that range policy performs significantly better than the MD range policy. And after Damien and Christian's talk yesterday, I recompiled and ran it with 5.02. And this was the result after that as well. The next thing is let's split it up. Now, the key thing that I wanted to mention here, gradient is, yes?
The acceleration is in 5.1, it's not in 5.2.
Sorry?
The optimization is in 5.1, not in 5.2.
OK, cool. Thank you. So the next one is, the next thing I want to state is we can't really use range policy and MD range policy because gradient is not our final output, and we don't store it to global memory. We want to use a temporary variable to store the gradient. So obviously, the next thing to do is to use team policy and team thread range. So we split all the elements over team policy, all the quadrature points over team thread range, and in between, we allocate a scratch view. And this is essentially the canonical example that Christian presents in his talks, where you split the elements over team policy and quadrature points over team thread range, and the scratch view, allocate a scratch view per element, right? And we do see improvement over from going from team policy to team policy with scratch views. And at this point, I was comparing the results. This was about a couple of years ago. At this point, I was comparing the results to the CUDA version of the code, and the performance was not that great. And this was around 2023, around the first Kokkos user group meeting. And Kim Lejoie at that time suggested some optimizations that I could do. So the main problem there is, let's consider every team policy gets a single element, right? Let's consider if I'm in 2D and I have 8 quadrature points per dimension. So the total number of quadrature points are 64. So in that case, I do not have, and in CUDA especially, a team is assigned to a block. So essentially, we don't have enough parallelization that we can use for that team. So the obvious goal was to increase the parallelization, right? So rather than doing a single element per team, we chunk up the different elements in a single team and loop over all the GLL points per chunk. And this essentially performs well. So, and the chunk size in CUDA, we choose to be 32 so that we don't get warp divergence. But this also works really well when you have SIMD intrinsics, because now I can set up the chunk size to be SIMD size and loop over the element using extrinsic SIMD vectorizations. But in this case as well, like I have 32 elements, and let's say if I'm in 2D, I have 64 GLL points or 64 quadrature points. That works fine in 2D. But when I move to 3D, I have 512 quadrature points, and that limits the amount of scratch memory I can use, because that does not fit into scratch memory. So I need another degree of freedom that I can use so that I can optimize for scratch size. And the way we do that, or the way I implemented this over here is, on top of chunking, we also enable tiling. And within the Kokkos kernel itself, we loop over with the tiles. So essentially, our kernel looks something like this, right? So I loop over all the chunks using team policy. I have then I allocate my scratch views. Then I have 2 compile time loops that loop over all the tiles. So that essentially means that they move this tile across this matrix. And finally, I have the team thread range. And if you see over here, I'm allocating the scratch view outside of the compile time for loops. With that, we got significant speed up, right? So with team policy and chunking, we get to about 86 microseconds. And with tiling, we get to about 67 microseconds. And this was great. We were right now faster than the CUDA version of the code. However, about 3 months ago, I stumbled onto this library called CuTe, which is part of the Cutlass ecosystem. And I wanted to experiment how that compares to Kokkos, right? So the way they state it is CuTe is a C++ template abstractions for defining and operating on hierarchical multidimensional layouts of threads and data. In layman terms, what that essentially means is they have templates for defining views and how to lay out that view, but they also have mathematical operators that is able to tile that view or divide that layout across blocks, then divide that block across tiles, and divide that tile across threads. And to make an apples to apples, and CuTe also has instructions for doing MMA, ways to do MMA instructions or specialized MMA instructions. But in this case, the comparison is just with 128-bit copy and FMA instructions. So the next result is with that. So with that, I see about 56 microseconds compared to 67 microseconds. And the reason for that, I think, is, so let's look at the Kokkos version, right? So I launch my team policy. I allocate my scratch view somewhere in between over here. Then I load from global to shared. I have a team barrier, compute the gems, store, and then iterate over the next tile. However, the main performance bottleneck, or most of the time, is spent in loading from this global to shared memory. And this sync threads ends up being a problem there, right? The way the CuTe algorithm works is I launch the block, in this case. I load from global to register memory. So I prefetch tile 0. Then I load that tile 0, like the register, to shared memory. This is a fast operation. And then I compute the gem and the store. But while I'm computing the gem and the store, I'm also loading the next tile from global to register memory. And at that point that we are getting instruction level parallelism. And this operation in the next tile ends up being much faster because it's just loading from register memory to shared memory. And I could not replicate this pattern in Kokkos in a performance portable way. So some key takeaways, right? So in hierarchical parallelism, some obvious things. If you have to use, like if you have random accesses, use scratch views. You will get much better performance. Make sure you have enough parallelism. What I've seen is for decently sized kernels, Kokkos Auto always chooses 128 or 256 threads per team. And if you do not have enough parallelism to work on that, you're essentially wasting some resources. For tiling, use const_expr constants when you can for your tile sizes, and make them powers of 2, because at some point of time, you might have to cast a linear index into a multidimensional index. And the compiler is just going to be happy doing that as powers of 2. Range policy versus MD range policy, seems like I need to switch to 5.1. This is the reason I couldn't figure out how to implement the CuTe kernel in Kokkos version, because Kokkos doesn't have semantics for what is work items per thread, and that is essentially backend specific. And to be frank, I think the CuTe version implementation would work worse with on CPUs. And lastly, I also wanted to experiment with Kokkos-kernels, because essentially what we have are batched gems, but I couldn't get to it. I do want to experiment with that when I get back. Yeah, that's it.
Thank you, Rohit. Are there any questions? We have a good amount of time.
Yeah.
That asynchronous copying into shared memory, is that just using these RDMA engines and what do we call it, the TMA engines or whatnot?
No, it's not. So this version does not use it. Like I made sure that I'm just using a universal. So what they call.
No, I mean, how does that asynchronously work? Is that like warp specialization, or is it?
So it's using more registers than the other one. So this
No.
kernel is actually using more registers to make sure that it's available, right? So my occupancy is much lesser for this kernel. But
Oh, so you essentially initiate loads into register,
Yeah.
and while that happens, you start the gem stuff and hope that that overlaps.
yeah.
Okay. Yeah, no, the way we've been looking at that is there's actually units to do this in modern NVIDIA GPUs. We just don't really expose them yet. In principle, the hope would be that an asynchronous deep copy call before you start the gem would essentially do that within the team. But okay,
Exactly.
thanks.
So they also have CPA syncs that you can do on A100s, for example. But I just wanted to make sure that apples to apples comparison.
All right. Any more questions? That doesn't seem to be the case. So let's thank Rohit again.